A rock thrown into a pond. It disappears beneath the surface without a trace. A coin dropped into a glass of water. It falls with a silent finality to the bottom. A simple, undeniable truth of our world. Things that are heavy, things that are dense, they sink. It's a truth we've been taught since childhood. But then, we look at the ocean. And there it is, a sight that defies all logic. A vessel of immense size, made of thousands, perhaps millions of tons of steel. An object that, if you were to take a single cubic meter of its hull, would plummet to the ocean floor in an instant. And yet, this colossal object, this monument of metal, glides gracefully across the surface of the water. It floats. The story, as all great stories do, begins with a single question. A Greek mathematician named Archimedes was tasked by King Hiero II of Syracuse to determine if his new crown was made of pure gold or a cheaper alloy. The problem was, Archimedes couldn't damage the crown to find out. While taking a bath, he noticed something. As he submerged his body, the water level in the tub rose. The more of his body that went in, the more water overflowed. He realized that the volume of water displaced was equal to the volume of his body. And so, the legend goes, he ran naked through the streets, shouting, "Eureka!" or "I have found it." But Archimedes discovered something more profound. He discovered that an object immersed in a fluid is acted upon by an upward force called the buoyant force. This force is equal to the weight of the fluid that the object displaces. This is the cornerstone of everything we're about to discuss. This is the law that allows ships to float. So what does this mean for a ship? A small, solid piece of steel will sink because its weight is greater than the weight of the water it can displace. But a ship is not a solid block of steel. A ship is mostly empty space. The genius of shipbuilding is not just in the strength of the steel, but in the shape of the hull. A ship's hull is a massive, hollow bowl. When this massive bowl is placed in the water, it pushes a huge volume of water aside. The weight of this displaced water is enormous. If the ship's total weight, which includes the weight of the steel, the cargo, the engines, the fuel, and the crew, is less than the weight of the water it displaces, the buoyant force will be greater than the ship's weight, and it will float. Think of it like this. Take a small, heavy ball of clay, drop it in water, and it sinks. Now, take the same ball of clay, with the exact same weight, and mold it into a hollow bowl. Place that bowl gently on the water, and it floats. Why? Because you have increased its volume without changing its weight. The bowl now displaces a much larger volume of water, and the buoyant force acting on it is now greater than the clay's weight. The ship is just a colossal version of that simple clay bowl. This principle, so simple and yet so revolutionary, is the foundation of every ship ever built. But the story gets more complex and more fascinating. Because what if you wanted to control this force? What if you wanted to make a ship sink and then rise again? This is where the submarine comes in. A submarine is a testament to our mastery of Archimedes' principle. It has massive ballast tanks. To sink, it opens valves and lets water into these tanks. As water fills the tanks, the submarine's total weight increases, while its volume remains largely the same. Eventually, its weight becomes greater than the buoyant force, and it sinks. To rise again, the submarine uses compressed air to blow the water out of the ballast tanks. Its total weight decreases, becoming less than the buoyant force, and it rises to the surface. It's a precise, calculated dance with the laws of physics. The ability to control its weight and buoyancy is what allows it to navigate the depths of the ocean. But a ship is not just a hollow bowl. It's an intricate work of engineering. The shape of the hull, for instance, is not just about displacing water. It's about stability. The bottom of the hull is where the center of buoyancy lies. The center of gravity, which is the ship's total weight, lies somewhere else. For a ship to be stable, the center of gravity must be below the metacentric height. Engineers spend years perfecting the design of a hull, using computer simulations and scale models to ensure that a ship, even when tossed by immense waves, will not capsize. They design massive rudders to steer, propellers to propel, and countless bulkheads and watertight compartments to ensure that if a section of the hull is breached, the entire ship won't flood and the buoyant force won't be compromised. Every cargo ship, every cruise liner, every warship is a testament to this level of detail. Their hulls are carefully designed with sleek, hydrodynamic lines to reduce drag and increase fuel efficiency. The steel itself is not just a solid block. It's a complex latticework of beams and plates, welded together with extreme precision to distribute weight and withstand immense pressure. This is the art of shipbuilding. It's the application of scientific principles on a scale that is staggering. The history of this paradox is a story of human faith and skepticism. For thousands of years, ships were made of wood. Wood floats naturally because its density is less than that of water. When an English ironmaster named John Wilkinson built the first iron barge in 1787, people thought he was mad. "It will sink like a stone," they said. But it didn't. The barge floated perfectly, proving that it wasn't the material that mattered, but the design. Still, the idea of an iron ship was too radical for most. It took decades for the idea to take hold. The turning point came with the launch of the SS Great Britain in 1843, a massive, steam-powered, iron-hulled ship. It was a marvel of engineering and a symbol of a new era. It showed the world that with a deep enough understanding of science, we could transcend the limitations of our materials. We could take the same metal that sinks to the bottom of the sea and transform it into a vehicle of exploration and commerce. But this new faith in science and engineering would face its ultimate test. The story of the Titanic is a tragic one, but it is also a story about the limits of this paradox. The Titanic was the largest, most luxurious ship of its time. It was hailed as unsinkable. This was not just a marketing slogan. It was a belief based on sound engineering principles. The ship had a double bottom and 16 watertight compartments. It was designed so that it could stay afloat even if 2 of its compartments flooded. But on that fateful night in 1912, it struck an iceberg. The impact created a massive gash that was over 300 feet long, compromising not just 2, but 6 of its compartments. As water rushed in, the ship's weight rapidly increased. The buoyant force, which was keeping it afloat, was no longer strong enough to counteract the massive influx of water. The ship, once a symbol of human triumph over the sea, was now a victim of its own weight. The Titanic did not sink because the principle of buoyancy was wrong. It sank because the principle was compromised. The hollow hull, the very thing that allowed it to float, was no longer hollow. The paradox of the floating ship was a paradox of design, not of nature. And so, we return to our initial question. Why does a ship made of steel float? The simple answer is Archimedes' principle. The more profound answer is that it's a testament to human ingenuity. A ship is a physical representation of our ability to see a problem, a heavy, sinking material, and redefine its terms. We didn't change the material, we changed its form. We gave it a new purpose. We took a substance that is denser than water and, by shaping it, by understanding the forces around it, we made it buoyant. The ship's ability to float is a beautiful and elegant metaphor for our own lives. We are all filled with our own kind of weight and density, our fears, our failures, our struggles. But like the ship, our ability to stay afloat isn't about the weight of our problems. It's about our volume, our structure, and our ability to displace the challenges around us. A ship floats not because it's light, but because it is an intelligently designed container for empty space. And perhaps, in our own lives, finding our way through the rough waters is about learning to be a container for the things that would otherwise sink us.